In this video we will be discussing an example for Euler's method, and we know that Euler's method is used to solve differential equation numerically. So in this example we can see two main equations that we already discussed in the theoretical part of the Euler's method. So first equation is for x values and the second one is for y values. And the first one is we can see xn equal to xn minus 1 plus h. So the xn minus 1 is the x value which is just before the nth position or the nth value. Okay, so the nth value of x will be equal to n minus 1th value of x plus h, so where h is the small step size. So for example it can be 0.1, 0.2, 0.3 etc. in any values, and when it is very small, the solution will be more accurate. So if you are having an h value, then if you want to find out what is the next x value, then you have to use this first equation. Okay, that will give you the nth x value from the n minus 1th x value. And the second one is the value of y, that is the solution of our differential equation. So in order to find the solution at different x value, we have to use this second equation, where we have yn equal to yn minus 1 plus h into f of xn minus 1 comma yn minus 1. So here we have to find out what is the value of y at nth position, okay, or what is the nth y value, which will be given by the n minus 1th y value added with h star the given differential equation at previous point, that is xn minus 1 and yn minus 1. So if you use this equation, then we can find out what is the y value at nth y value. Okay, so that is our solution. For example, if you have given initial condition like this, y of 0 equal to 0, which means that the first value of y is equal to 0, or initial value of the y is equal to 0, and initial value of x is also 0, because what is given in this bracket, this one is your x0 or your initial x value. So your x0 is 0 and your y0 is also 0. That is the initial condition, and you have given this differential equation here. So this differential equation is dy by dx equal to x plus 2y, and which we have again labeled as f of x y in terms of a function. So we are actually giving f of x y, which is equal to dy by dx, and which is equal to x plus 2y. Now if you want to find out what is the value of y of 0.4, which means that when x becomes 0.4, what will be the value of y for this particular equation. Okay, this particular equation, for this particular differential equation, if you solve this particular differential equation, what will be the value of y at x equal to 0.4, that we have to find out. Okay, so in order to find out this, we have to go through some steps that is described in this side. So first we have to consider different x values, and correspondingly what will be the y value that we have to calculate. So we have x0 equal to 0 and y0 equal to 0, that is the initial condition that we already got from here. So we have x equal to 0 and y equal to 0, sorry, x0 equal to 0 and y0 equal to 0. Then we have to move to the x1. So x1, we already know that x1 will be equal to xn minus 1, that is your previous x value. So that means x1 will be equal to x0 plus h. So this will be equal to x0 is nothing but 0 plus h is, for example, if you take 0.1, so let's take h equal to 0.1 here for this case. So this will become 0.1 and your x1 is nothing but 0.1. So that's what we have given here. Okay, so if you are reducing the step size, you will be getting more accurate result that we will discuss later. Okay, so we have x1. So then you substitute that x1 value in this f of x n minus 1 y n minus 1, that is differential equation, and if you substitute that value, then you can find out what is yn. So your y1 will be nothing but yn minus 1, that is your y0, okay, plus h into f of x minus 1, that is f of x0 comma y0. So this will be your y0 is nothing but 0 plus your h is 0.1 into f of x0 y0. Okay, f of x0 y0 means you have to substitute the value of x0 and y0 in this differential equation. That means x plus 2y. Okay, so your x0 is 0 and y0 is 0, so x plus 2y will be equal to 0. So this term becomes 0. So the total y1 value is 0. Okay, so then we have y1 equal to 0. Then we have to go to the next step, that is for x2, what will be the value of x2, and you substitute in the same way. In that time you have to give here x1 plus h, and you will be getting 0.2 as your x2 value, and then we have to calculate what is the y2 value, and y2 will be given by equation that is y1, that is you have already given here. So yn minus 1, which will be y1 plus h into f of x1 comma y1. So if you calculate this, you already know what is y1 is 0 plus 0.1 into f of x1 y1. x1 is 0.1 and y1 is 0. So x1 is 0.1 means you will be getting your y value, that is x plus 2y becomes 0.1, right? Okay, so if we multiply these two, then you will get 0.01. So that's what we are getting here. So in the same way, you have to go up to x4 equal to 0.4. That's what we have to find out, the value of y at 0.4. That means x becomes 0.4 with step size h equal to 0.1. So in that case, if you follow the same procedure what we have discussed here, this procedure, then we can get y4, that is y of 0.4 will be equal to 0.0684. So this is how we do the Euler's method, and how we find out the solution of the differential equation at different x value. And if you plot this kind of curve, how it is going to come, so it will be, for example, your actual curve is like this, then if you'll be getting different points like this, and if you join this point, then you'll get the numerical solution. So there will be a slight difference from the original solution, but it will be much more accurate. If you are reducing the step size, it will be much more accurate too, because if you are using steps like very close to each other, then it will be going like this. Instead of that, if you are choosing a step like this, then the line will be going like this, and your original curve will be like this. So the accuracy will be larger for small step size, or the value of when the value of h becomes smaller. So that's all about this example for Euler's method. Thank you.